Thank you. I'd like to thank Professor Hamanaka-san for inviting me. I only wish I would be able to be there in person, because what I'm going to describe has many open problems, and I'm sure if we were meeting in person, this would start a number of collaborations. So if you're interested in any of this, let me know. So I'm going to describe today how monopoles can be actually very useful in exploring gravitational instantons and how they connect to each other. Let me first describe some ambiguity that exists in the literature. So first, in all of these talks, the spaces we are going to consider are Riemannian four manifolds. And we will, for all of them, require that they have a square integrable Riemann curvature tensor. So the notion of gravitational instantons was introduced by Hawking in '77, and I believe the person who introduces the notion has the right of defining it. So Hawking defined gravitational instantons to be Einstein manifolds. So any solution of vacuum Einstein equation in Riemannian signature and with finite Pontryagin number, or square of integral of Riemann tensor, is a gravitational instanton. Unfortunately, in mathematics recently, this term was used in other slightly more restrictive meaning. So then, among gravitational instantons, there are self-dual gravitational instantons. And these are Riemannian manifolds, again with square integrable Riemann tensor, whose Riemann tensor, considered as two-form, is self-dual. Locally, because of this condition, this manifold is hyperkähler. But this condition might not be satisfied. It might not be hyperkähler globally. So the main interest of this talk is studying hyperkähler manifolds, or hyperkähler gravitational instantons. In other words, we look at hyperkähler manifold with square integrable Riemann curvature. So complete hyperkähler manifold of real dimension 4 with square integrable Riemann tensor. So there's a natural question. Now, that's an example of gravitational instanton, but what should we call it? Well, locally, the structure is quaternionic, so it has to do with quaternions, so we can't call it quaternion, that name is taken. Quatron doesn't sound good. Twiston, since it has to do with twistors. Hamilton, none of this works. So to emphasize relation to quaternions, maybe you should just use another language. And 4 in Greek is Tesseros. So I suggest calling these Tesserons. So a Tesseron is a complete, non-compact, hyperkähler manifold of real dimension 4 with square integrable curvature tensor. And this would avoid any ambiguity if we use a separate notion. So the goal of this talk is to understand what sort of Tesserons are there and how they connect to each other. And the main tool in understanding this was realizing each tesseron as a moduli space of monopoles. So fortunately, by now, there is a complete classification of tesserons. They come in various kinds, which I'll explain in a second: ALE, ALF, ALG, and ALH. And there are results, like Tarelli type theorems, established for each of these classes, with some caveat, which I'm going to highlight. But essentially, we know all of them by now. So these classes are determined by the volume growth. You pick one point in the manifold, you fix it, and then you look at a large ball of radius r and compute its volume. And you ask, how does this volume changes with radius? If it grows maximally as r to the fourth, that space is called ALE. Sometimes it's called asymptotically locally Euclidean tesseron. If it grows cubically, then we call it ALF. If it's quadratic, we call it ALG, and if it's anything less than quadratic, it's ALH. As it happens, for all these tesserons in the classification, they asymptotically possess a local symmetry. They have asymptotic triholomorphic isometry. Isometry which respects all of the three complex structures, respect hyperkähler structure. Then, according to Gibbons and Hawking, any hyperkähler manifold of 4 dimensions with an isometry which shifts one of the coordinates, so sends tau to tau plus epsilon, has to have this form where V is a function on a piece of three-dimensional space. And this function is such that it is dual to a connection one form. And as a result, this function V is harmonic. So if it is a function on R3 base, then asymptotically it can have this form. So some integer over 2 times the distance. In this case, you get quartic volume growth, and this is an ALE space. Or it could be a constant plus 1 over distance. In that case, the space is ALF. Or it could behave as a logarithm or as a linear function. So currently in the literature, there's distinction between ALG and ALG star spaces. And whenever n is not 0, in other words, when V actually, asymptotic V has some non-trivial dependence on the coordinates, then people put star on those. And if n is 0, then they don't use stars, and it's ALH or ALG. So in other words, these cases without the stars have n equals 0, therefore they have locally constant fiber. So let's get some better understanding of what these spaces look like. So ALE spaces, prototypical example of ALE space is R4. And R4 flat metric in radial coordinates can be written this way, where this theta is the coordinate along the Hopf fiber. So if R4, you fix the radius, then it is a 3-sphere, and you can Hopf fiber this 3-sphere. This is coordinate along the fiber. Again, it's a local coordinate. Of course, there's no global coordinate along Hopf fiber because the fibration is non-trivial. So again, this is just usual Euclidean metric written in these coordinates. So asymptotically, it is a circle, and the radius of the circle, the period of the circle grows as you increase x, and grows indefinitely. So the circle fibration with a growing circle fiber. All of these spaces really asymptotically look like a quotient by a finite subgroup of SU2 of R4. And this was proved by Cronheim. ALF space looks somewhat similar. Prototypical ALF space is the Taub-Nut space, which topologically is again R4. And the metric looks fairly similar. And now you can see as x goes to infinity, the size of the fiber is finite. So it is a circle fibration with stabilizing circle. ALG and ALH spaces are elliptic fibrations. This is the case where you have a torus fibered over a plane, and the geometry is given by one asymptotic geometry is given by one holomorphic function, and the harmonic function that figures in Gibbons-Hawking metric is the imaginary part of this holomorphic function. So the difference is that for ALG case, it behaves as a logarithm, and for ALH case, it behaves linearly. As a result, it has ramifications for what kind of base it is fibered on. So this fiber is a torus with periodic coordinates theta A and theta B. And this torus, in first case, in the ALG case, is fibered over an asymptotic cone. So this Z coordinate is coordinate on a cone, asymptotic. And for ALH spaces, it is fibered over asymptotic cylinder. And that is what explains the different volume growth for these two cases. And here is the classification within each class. So out of ALE cases, well, in all of these classes, there is a kind of a trivial example which separates into a direct product, namely R4, R3 cross S1, R2 cross T2, and R cross T3. These are too simple in a class of examples. They don't really give you good understanding of what the other asymptotics could be. And that's why I kind of shade them out. And potentially from the definition of Tesserons, we should exclude this. We should exclude all the spaces which are just products, metric products. So then if we did exclude them, then ALE spaces come in types A, D, or E, where the index in A, these are two infinite families, and then there are 3 examples of E spaces. So in this convention, like you can call R4 as a 0 space, and then A1 is the Iguchi-Hansen metric. ALF spaces come only in A and D types, and now here K varies from 0 to infinity over integers, and D varies from 0 to infinity. You can see that there are 2 extra spaces here. And A0 space is the Taub-Knot, a non-trivial gravitational instanton now, non-trivial Tesseron. And a K case is the Taub-Knot, but with K+1 centers. And in low dimension, so for low K, D0 space, D0 ALF space, is the Atiyah-Hitchin space. And D1 is a deformation of its universal cover. D2 space itself is rather special. Asymptotically, it actually has locally constant fiber. And there's a deformation of a quotient of R2 cross S1 mod Z2, where Z2 inverts all 4 coordinates. So I do not quite like this notation with stars, but in this case, this would be the only ALF case, and everything else should have stars, ALF stars, and all of ALE spaces are ALE stars. So it's a little, unfortunately, star is on the wrong space, but by now it's a convention. Now let's look at ALG spaces. ALG spaces come as a D family, only 5 of them, from 0 to 4. Then there are 3 E-type spaces, and they're mirror duals. That's why I call them Shah spaces, because as you know, mirror symmetry inverts along the diagonal of the Hodge diamond. So if you reflect E, then you'll get Shah. And indeed, there is a mirror relation between the 2 families. And then ALH spaces come in this E series, plus there is another E1 tilde. And finally, the last one is what I call half K3, and that's the ALH space, the one that has locally constant fiber. What will be important for us today is to count not only the moduli space, so its type, but also how many parameters does it have. In other words, how many changes can I make to it, or deformations can I make to it, so it is still Tesseron, but a different one. So in a sense, I count parameters which specify the geometry. And the way I'm going to denote it is M sub n, where n denotes the number of real parameters specifying the infinity. For example, in the Taub-Knot space, there is size of the circle. So n counts the number of parameters in infinity. And once you fix these parameters at infinity, then remaining parameters are the interior parameters. So for example, R4, well, doesn't have any parameters, either at infinity or in the interior. A K space generically has 3K interior parameters, AK ALE space, and doesn't have any parameters parameterizing asymptotic. And same for D and for E. And this K here, well, we'll talk about this K in a second. R3 cross S1 doesn't have any interior parameters, but has one parameter, which is radius of this asymptotic circle. Well, this circle, it's the same circle everywhere. And for ALF cases, again, they have 3K parameters in the interior and one parameter specifying infinity. And then you can see for ALG, by now it's a theorem. And in this case, we know these deformations, and I suspect that this is all there is, but at the moment, that's why there's question mark, this is not a theorem yet. These symbols, the blue symbols here, they correspond to, now all of the spaces are elliptic fibrations, they correspond to, once the fibration is maximally degenerate, what kind of Kadaira fiber it can have in the interior. So next, ALH spaces, again, form this EK-type series, and the number of internal parameters is again 3K, and there's 3 parameters at infinity. While half K3, for example, or R cross T3 have 7 parameters at infinity. That parameterizes the shape of the 3 torus at infinity. Right? So if you have a 3 torus, then you need to give 3 vectors in space, but then one of these vectors can be rotated so it is along the x-axis, for example, in 3-dimensional space. And as a result, there's 6 other parameters specifying the vector and the length of the first vector along the x-coordinate. So that's why you have 7 parameters. Now, I gave the naive count of parameters here, and that will be useful in understanding how the spaces connect together. But in reality, of course, there can be some extra symmetries. For example, A1 ALE space doesn't have 3 parameters really. Like, where did 3 parameters come from? You can take 3 symplectic forms of hyperkähler structure and integrate it over one non-trivial sphere inside of Iguchi-Hansen space. That gives you 3 numbers. But whenever the sum of squares of 3 numbers equal to some other sum of squares of some other triplet, there is a rotation which takes one of these spaces to another. So these spaces are really isometric. So the real count should be 1 sub 1 rather than 3 sub 1. And same for ALF. Now, there is a certain miracle happening with these spaces, namely ALG and ALH spaces correspond one-to-one to classification of Plenary equations, namely discrete Plenary equations. If you look at the tables that I presented to you of these spaces, they correspond exactly to the spaces you can find in this work of Hidetaka Sakai and Naomi and collaborators. So each of these spaces corresponds to some Plenary, either rational, trigonometric, or elliptic. And I suspect that functions that appear in this Plenary will be directly relevant to the geometry that we're trying to describe. But another big advantage is just from this table, you can read off the corresponding Hitchin system, whose modular space is related to these spaces. This Hitchin system is a form of non-transform of the corresponding monopoles that I'm going to describe next. So the main subject of the talk is how to realize the spaces as modular spaces of monopoles. At the moment, at this moment in the talk, ALE spaces of A, D, and E type don't appear to be natural modular spaces of monopoles. But ALF spaces can have very, well, almost immediate interpretation. As we'll discuss in a moment, R3 cross S1 is modular spaces of one monopole in R3, while D0 and D1 spaces modular spaces of centered two monopoles in R3. With Kapustin a long while ago, we studied centered two monopoles with prescribed simple Dirac singularities, and their modular spaces, as we showed, is DK space. And if you look at a single BPS monopole in R3 with K Dirac singularities, you will end up, I'm sorry, there's a mistake here, with K plus 1 Dirac singularities, you will end up with AK ALF space. Next to ALG spaces. ALG spaces as modular spaces of monopoles. Again, a while ago we described with Anton Kapustin by studying periodic monopoles. From periodic monopoles, modular spaces of two periodic monopoles with singularities are of D type, and two monopoles in SU2 can have, well, in U2, can have up to 4 singularities. And that's how you get this series, D0 up to D4. Also with Anton, we realized E-type spaces as equivariant instantons on R2 cross T2. And I'll describe in a little bit more detail later how these emerge. But still, these are instantons and not monopoles as such. And SHA spaces can have similar realization, in fact. For ALH spaces, with my student Rebecca Cross, we studied these spaces and computed their asymptotics all the way up to E6. So this work originates in our collaboration with Richard Ward. And then I classified these spaces, and 2 spaces were missing. And on Friday, you can hear from Thomas Harris of how to construct E8 and E7 spaces also as modular spaces of monopoles. And finally, there is the half K3 space, which asymptotically looks like R cross T3. And these was studied in detail by Charbonneau and Hurtubise. And before that, with Marcos Jardim, we realized this as modular spaces of triply periodic monopoles of charge 2 with positive and negative singularities. So, well, in this meeting, you don't have to describe what monopole is. I'm sure everyone knows it well. I just put it on the page that for us, the manifold on which we study monopoles is important. So there's any Riemannian 3 manifold with metric G. You have Hermitian bundle over it, and you have a pair, connection and skew Hermitian endomorphism. And they satisfy the Bogomolny equation that covariant differential of the endomorphism is Hodge dual to the curvature of the connection. The relevant spaces for us will be R3. In that case, we talk about a monopole. If you talk about monopole on R2 cross S1 of radius R, then you would call it a periodic monopole. Sometimes these are called monopole chains. And if you talk about monopole on R cross a torus, then it's a doubly periodic monopole, or monopole wall, or monowall. So a torus here has 3 real parameters, namely it has its volume, for example, and tau, its shape or a complex structure. And corresponding modular spaces, as we are going to see, have the type ALF, ALG, and ALH. Next, to really have the full richness of these monopoles, we need to allow some singularities, some Dirac singularities. So they're quite mild, and they will not spoil the completeness of our metric in general. So on whatever space you consider, you select some points, P1 up to P nu minus and P1 up to P nu plus. And these will be negatively charged points, positively charged points, and you allow the Higgs field at the corresponding point to go off either to plus or to minus infinity, depending whether it is positive singularity or negative singularity. More generally, the charge here doesn't have to be to have this form. It can be any co-character in the corresponding gauge group, and perhaps Thomas on Friday will talk about some of these. Next, the boundary conditions. Boundary conditions are absolutely crucial in this story, and it's important to specify just the right boundary conditions so that the metric on the modular space is actually well defined in this hyperkähler. So on R3, there's this traditional asymptotic condition on the Higgs field, is that asymptotically it is gauge equivalent to this diagonal form with asymptotic values lambda minus lambda, and if monopole has charge q, it has this subleading term. So in particular, finite energy means that still the center of mass of this monopole can move, and it has an L2 deformation. At the same time, if you look at monopoles on R cross S1 with a complex coordinate on R2 given by x plus iy, and then var phi being periodic coordinate along the circle, now the Higgs field asymptotically behaves logarithmically. As described in our paper with Kapustin, it's not enough to fix the first 2 terms. You also have to fix the next subleading term. And it's easy to understand physically why this has to happen. because once the Higgs field behaves logarithmically, any deformation of this, even if you have one monopole solution, periodic monopole solution, then it doesn't have finite energy. The implication of this is that changing the position of the center of mass of the monopole is not an L2 deformation. And in fact, fixing this subleading term, it's the subleading term which knows about the position of the center of mass. Once you fix these parameters, then you do have a good problem, and the moduli space, so all solutions satisfying these boundary equations, will form a hyperkähler manifold. So again, in this case, you don't have to fix the center of mass. The very problem itself, or these asymptotic conditions, will fix it for you. And if you didn't fix it, you'll discover that some directions, some deformations are not L2. Next, for doubly periodic monopoles, we'll have coordinate x on real line and two periodic coordinates on the torus. In this case, Higgs field can behave linearly. We fix the subleading term, the leading terms, and the corresponding connection with subleading terms in monodromy. Again, of course, this will have infinite energy, and as a result, center of mass will be fixed automatically. So let's talk a little bit about the moduli space of monopoles in R3. This is by now a well understood subject. And if you look at a single monopole in R3, well, that monopole, this asymptotics, would have a position of this monopole that gives you three parameters, and it also has a phase once you fix the framing at infinity. What is important, so the moduli spaces will be R3 cross S1, and what I'd like to emphasize is that this lambda, the asymptotic value of the Higgs field, will determine the radius of this circle, which is 1 over root lambda. So again, the size of the circle at infinity in these moduli spaces is determined by the Higgs field expectation value at infinity. Physically, this lambda is the symmetry breaking parameter at infinity. So next, one can look at a single monopole with prescribed k+1 simple Dirac singularities. So if this star stands here for monopole and it has three positions and some phase, then at k +1 points, p0, p1, p2, and so forth, pk, we specify Dirac singularities. So then it still has three positions in the phase. And moreover, these solutions were explicitly found, first with up to two singularities. We found it with Brian Durkin, and then with all singularities we found with an undergraduate student at the time, Chris Blair. And one can compute these. Well, there are many ways of computing these moduli spaces. So with Anton Kapustin, we derive this moduli space by looking at its twistor space and corresponding scattering problems. But then one can also do it directly. And you will get an k ALF space, which is multi-taub knot with these k+1 centers. Next, looking at two monopoles. This is the problem completely solved by Atiyah and Hitchin. With two monopoles, you now have, well, each of them has four moduli, so 4 parameters for moduli. So you get an 8-dimensional space. But this 8-dimensional space has a symmetry. It has a triholomorphic isometry which rotates the total phase of this configuration. So you can perform hyperkähler reduction. And hyperkähler reduction centers these monopoles. It fixes the position of their center of mass. So once you centered the monopoles, then you have a 4-dimensional space. And Atiyah Hitchin studied this space, and this is D0 ALF. And they found explicit metric on the space. As we then found with Kapustin, that if you introduce the singularities, then they will modify your moduli space to, if you introduce k singularities, you will get dk ALF space as a moduli space. So this monopole realization of moduli space suggests a very direct relation between these spaces. Namely, you can now start moving some of these singularities to infinity, making them collide, or changing the center of mass and moving center of mass to infinity. So let's have a look what happens in this case. Let's say we start with a single monopole with k+1 singularities. We know that this is an AK modulus. But now I take one of these singularities and move it off to infinity. Well, in whatever direction you prefer. What will happen in the end? I will be left with k-1 singularities. And as a result, in this limit, when pk is sent to infinity, my moduli space, AKLF, will degenerate to AK-1ILF space. And then I can continue this game. I can start moving the singularities one by one to infinity. And as a result, I'll keep degenerating the space until all of them are moved to infinity, and I end up with a single monopole moduli space, which is R3 cross S1. Well, needless to say, I can play the same game with centered two monopoles. I can start moving singularities to infinity, and in similar fashion, dk+1 ALF space will degenerate to dk ALF space, and so forth. All the way to the point where I finally moved all singularities to infinity, and I will end up with d0ALF. Well, there's one more game I can play here. I can take the center of mass and move that to infinity, let's say to the left. Of course, if I move the center of mass to the left by keeping one of the monopoles here in my region, the other monopole will also move to the left at twice the speed. So finally, when C goes to infinity, the other monopole is gone. And from the moduli space of two centered monopoles, by moving the center to infinity, I will degenerate to a single monopole in the presence of as many singularities. For example, if I have two monopole moduli space, by moving the center of mass to infinity, I will end up with a single monopole in R3. Similarly, if I started with k+1 singularities, and I considered two monopoles in this background, then by moving center of mass to infinity, I will end up with one monopole with k+1 singularities, and this is AK space. So we have this diagram telling us how the spaces are connected. Well, not only that, we can, using this, kind of refine this connection, not just the diagram. If you have ALF space with fixed asymptotic size of the circle, that corresponds to studying one monopole with one singularity in R3. If you take that singularity to infinity, which, so along this axis, I'm going to plot 1 over the distance to the singularity. So sending it to infinity means moving to the origin of this line, and the origin of this line is R3 cross S1. What I'd like to emphasize again is that this is a little deceiving because A0 ALF doesn't have any internal parameters. So as a result, of course, all these A0 ALF spaces, all these taub nuts, are isometric. So one has to be careful when formalizing this mathematically and describing this cell complex. One has to include, for example, what you mean by isometries, or encode the position of the center in terms of, for example, subleading terms in the behavior of your metric at infinity. So next, if you look at A1 ALF with asymptotic circle of size L, and L is fixed for now, then that appears as studying one monopole in the presence of two singularities. So again, I schematically draw these two lines here, which is 1 over distance to first and 1 over distance to second singularity. Then, if I start with this problem by going down, namely by sending P1 to infinity, I will recover A0 ALF space. Likewise, going to the left takes me again to A0 ALF space. And then, if heading to the corner, amounts to taking both singularities to infinity. That's R3 cross S1. Along the diagonal here, there is, and this shouldn't be diagonal in this plane, this is diagonal in 6-dimensional space, which has all the parameters. So if two of these singular points coincide, not just the distances from the origin, but they literally coincide, then the space develops A1 singularity, and you can view this as taub naught of twice the size of the circle divided by Z2. Moreover, this whole space has isometry interchanging the roles of P1 and P2. So you should fold it along the diagonal. Slightly more interesting example, D2 ALF space. So that's a space, modulus space of two centered monopoles with two singularities. Now we can play a few different games. We can send one of the singularities to zero, we can send one of the singularities to infinity, or another singularity to infinity, or the center of mass to infinity. So as I described, sending of center of mass to infinity degenerates D-type space to A-type space. So D1 becomes A1 ALF. So D2 becomes A1 ALF. While sending only one singularity to infinity decreases the index. So D2 becomes D1. So if you're here in the bulk, this is D2 ALF space. And if you send one of the singularities to infinity, you get D1 ALF. And if you send the center of mass to infinity, you end up with A1 ALF. On the diagonal here, again, you have a singular space. But if you now take these 2 points and actually send P1 and P2 to 0, which in this case moving infinitely far in this direction, then the space degenerates to R3 cross S1 mod Z2. So specifically in this degeneration, you can see that this space is really has constant asymptotic fiber. Well, in other words, what we just described is relation in this plane. We described how ALF spaces are related to each other. But on top of them, we have ALE spaces. And so there's A series, there's D series. You might expect that they're related in a similar way. And there is also E. So what's the connection between these? Well, let's look at the simplest one. You have a monopole in R3. Asymptotic Higgs field tends to diagonal matrix lambda minus lambda, gauge equivalence class. And now we would like to get to R4. So, well, we can play with the lambda parameter, specifying infinity in our problem. It's fairly clear that sending lambda to 0 opens up the circle, and R3 cross S1 becomes R4. Similar story happens with the taub naught. If you start with modulus space of a single monopole with one Dirac singularity, sending lambda to 0 opens up the circle of taub naught, and it becomes R4. These two limits, I should emphasize, are quite different geometrically. So the way this R4 emerges is quite different in these cases. And exactly the same happens with all the other realizations in this case. So you can degenerate send lambda to 0 in each of these problems. And as a result, you recover ALE type modulus spaces as limits of monopole modulus spaces. The moral of this is that you can interpret at least A and D type of ALE spaces as modulus spaces of monopoles without maximal symmetry breaking coming from asymptotic Higgs field, but rather the symmetry breaking comes from this holomorphic charge at infinity. The fact that there is non-zero charge tells us that asymptotically the space still splits into two line bundles, the fibers splits into two line bundles, and those line bundles now are holomorphic, and their degree is this holomorphic charge. So indeed, all ALE spaces of A and D type can be constructed as modulus spaces of monopoles. Well, there's still this problem. How do you construct E spaces as modulus spaces of monopoles? Well, before we go there, let's try to in slightly more detail, visualize the relation between these spaces. So now we have extra parameter to play with. There is position of the singularity that we can send off to infinity, and that's moving to the origin. There's also position of the center of mass of two monopoles. And in addition, there is this symmetry breaking parameter L at infinity, or lambda. So if you start with D1 ALF space, which is a moduli spaces of two centered monopoles with one singularity, if you send singularity to infinity, then that in this diagram means moving to the left, you end up on this plane, and that is Atiyah-Hitchin space, just moduli spaces of two centered monopoles. If instead you send center of mass to infinity, while keeping one of the monopoles in the region, then you end up with a problem with one monopole and one singularity, and that's D0 ALF space. And if instead you send the symmetry breaking parameter to 0, then you will recover D1 ALE space. And you can follow this in various limits. The only thing you should be careful with, and that's why there are the scissors here, is that here in this limit you get R4, here you get R4, but these two limits don't commute. In a way, you get this R4 in two different ways. In one case, it becomes as limit, it appears almost as a limit of R3 cross S1, in the other as a taubnet. So again, this intuitive understanding allows you to write corresponding cell complex, which describes the moduli structure, the parameter structure, I'm sorry. So next, let's gain some understanding of ALG spaces. ALG spaces will emerge as moduli spaces of periodic monopoles. Periodic monopoles will asymptotically have this form. You can count parameters here. So there is a complex parameter, mu, and then there are 4 real parameters. So altogether there's 6 parameters. Usually parameters in hyperkähler geometry come in triplets. And indeed, 3 of them are actual parameters. If you change them, you change the moduli space. And the other 2 determine position of center of mass. So in other words, 2 moduli spaces with different center of mass, but everything else equal, are actually isometric. But nevertheless, for us, it's convenient to keep them, because then we can study various degenerations and limits. So the claim that we established with Anton Kapustin is that 2 periodic monopoles first can have up to 4 different simple Dirac singularities, and the space with k singularities is a dk ALG space. So this realization makes it clear that as R, this periodicity, goes to infinity, if you study 2 monopoles with fixed singularities on a space which with some large period, then as R goes to infinity, the space opens up to R3, and the limit of dk-ALG space, well, this was one monopole moving in the background of k singularities, becomes one monopole in R3 moving in the background of k singularities. So from this you can actually see this degeneration, and you can see how d-type ALG space degenerates into d-type ALF space. But still remains a question: what is the place here of E and SHA spaces? Well, I do not have at the moment direct realization of these as moduli spaces of monopoles, but I can describe them using these pictures I described as limits of such spaces. So instead, let me describe how these appear as moduli spaces of instantons, and then we'll study the limits of monopole spaces. So how to realize this E and SHA spaces? You need to consider instanton on R2 cross T2. And if you think of T2 as a complex line divided by a lattice, then this product admits a cyclic action of Zn. You can take both coordinates, one coordinate in the plane and another along the torus, and rotate them simultaneously. Except the fact that there's a lattice there, it restricts what kind of Zn we can what kind of rotations we can apply. So for any tau, we can always apply Z2, which inverts all 4 coordinates. Now at the origin of R2, there will be a torus which has these 4 fixed points. In fact, if you blow up these fixed points, you'll get exactly this diagram. The torus divided by Z2 will be a new P1, and each of these points will be A1 singularity, which after deformation or blow-up will give you another cycle. So the intersection diagram of this space will look like this. Now, if you want to act by any other Zn, well, the lattice has to be invariant with respect to that. So it happens only if your lattice parameter is very special. So if it is at row point, 6th root of unity, then you can act with Z3 or Z6. And if it is I, so you have square as your torus, then you can act by Z4. In all of these cases, you can immediately see what the fixed points are, what their order is, and by blowing up or deforming, you can immediately read off the intersection diagram. And indeed, this is D and E type. So the claim is that if you study instantons which are equivariant under the section with these groups, then you will recover the Shah spaces. So what is important about this, maybe I'd like to emphasize, is that if you act by Z2, that is the D4 type of moduli space, then your tau parameter or the shape of the torus can be anything you like. For example, you can take one of the periods of the torus and send it to infinity, in which case the torus will degenerate into R cross a circle. So from studying such configuration, such moduli space, you can open up one of the circles and go from ALG type to ALF type. But in the other 3 cases, the shape of the torus is fixed. If you try to make one of the periods of the torus larger, then the other will invariably also become larger. So in this case, by making one period larger, the other will grow as well, and both directions will open. The moral is that if you have such ALG space, if you take its limit, it will jump from being ALG to being ALE right away. So the claim is that if you look at ALG spaces, which have E, D type, and Shah spaces, then the limits of these E-type ALG spaces will be E-type ALE spaces. So there's still this drawback. I aimed at describing everything in terms of monopoles, but instead I cheated. I described something to you as moduli spaces or instantons. So let me cure my misgiving here. And let's look at one level down. Let's look at monowalls. So you will have R cross a torus. I believe first such was studied by Kim-Young Lee. And then this group of collaborators used beautiful mathematics using amoebas and secondary polyhedra and so forth, describing these spaces. So first, let's look at abelian monopole. As I already mentioned, for abelian monopole, you have Higgs field, and its differential is dual to some connection, abelian connection, and that implies that Higgs field is harmonic. So harmonic function, unless it's exponentially growing in one of the directions on R cross torus, will look like a linear function, where Q, because it is dual to curvature of a connection on the torus, will have to be integer. And M is arbitrary subleading term. So that motivates what kind of problem we should consider. We look at the monopole with these asymptotic conditions, and we allow Dirac singularities. In this case, once you have higher rank, then the charges are no longer integer, but they're rational, and the denominator is just multiplicity of the corresponding degeneracy of the pair. So if I study such problem, then what do I have to specify? I have to specify these charges or the slopes of the rate of growth of my field at infinity. That gives me these lines with multiplicities along rational slopes. There will be some positive singularities where I'm going to draw these vertical lines where Higgs field shoots off to plus infinity, and some negative singularities where it shoots off to minus infinity. Once I draw this picture, I can actually draw an integer polygon corresponding to it. Namely, for each of these lines, I draw a perpendicular line whose length, integer length, in other words, it has rational slope, so it goes from one integer point to the next, and the number of integer points in which divide, or rather, the number of intervals into which this line is divided by integer points is equal to the number of eigenvalues of Higgs field with the same charge. So every horizontal line has integer length given by the number of positive charges, positive Dirac singularities, and this bottom line length, integer length, is given by the number of negative Dirac singularities. If you look at our paper with Richard Ward, then you see how this Newton polygon actually appears as indeed Newton polygon of some spectral curve. So once you drew this Newton polygon, it contains a lot of information. First, the slopes encode the charges. And second, if you want to know the number of moduli in the problem, then it's just 4 times the number of integer points inside of this Newton polygon. And if you want to know the number of parameters of corresponding space, then it is number of perimeter points minus 3 times 3. So that's the number of triplets that parameterize the shape of the space. Great. So, as I said, the number of moduli is 4 times number of internal points. And in this talk, we're interested in 4-dimensional spaces. So we need to look at all integer polygons which have one internal point. Well, there's infinitely many such polygons. So does it mean that there are infinitely many moduli spaces of monopoles? Well, again, as we argue with Richard Ward, there is SL2Z symmetry, which acts on this lattice, which at the same time acts as an isometry on monopole moduli spaces. The S generator of SL2Z corresponds to the Nahm transform. So if Nahm transform is an isometry, as it is in every known case, then two Newton polygons identified by changing of the axis by S transformation have exactly isometric spaces. And then T transformation corresponds to taking your monopole and adding purely abelian trace part. Adding any abelian part does not change the moduli space at all. So if you now classify Newton polygons with single internal point up to SL2Z transformation, you get these 12. Next, you can see exactly from this. For example, looking at this, you can see that this is a charge 2 monopole with 2 singularities, 2 positive and 2 negative singularities. By looking at what other equivalences you can get by adding purely abelian field, maybe with some Dirac singularities, you can see that all 3 monopole problems here are isometric. And again, here along each line, they will be isometric until you arrive at this line. Here you will have 2 different types. These 2 are isometric, and this is a different space. So as a result, we recover all these spaces, namely, well, how many? 1, 2, 3, 4, so 7 plus 1. So we recover 8 spaces, and you can also see how they are connected. Let me describe this connection in slightly more convenient terms. And that's where secondary polyhedron, introduced by Gelfand, Kapranov, and Zelevinsky, is very convenient. So, given a Newton polygon with all these integer points, you can first label these points, 1, 2, 3, 4, 5, however many there are. And then, for each subdivision of this polygon, you can get a vector whose dimension is n, the number of these points. For example, if you look at this subdivision, then the first coordinate of this vector, to read off the first coordinate, you need to look at the first point and sum up areas of all subdivisions, all, in this case, triangles, for which it is a vertex. So in this case, you get 5. Just to be clear, I consider this triangle to have area 1 rather than 1/2. So not to carry lots of 1/2 along. And then the coordinate corresponding to this point will be 1. It's the area of this triangle. So it's fairly straightforward how from any subdivision to read off the vector. The only other condition is that these subdivisions have to be regular. You cannot have kind of Escher raising stairs. So in other words, if you have this shape, and if this is your, I don't know, open air dance hall, and then you can build some columns above these of different lengths, and then you can throw a tarp on top and stretch it out, then the surface of this tarp will give you some subdivision, and only such subdivisions are allowed, which appear from this sort of plane arrangement. So the claim is that once you look at all these points, they will give you a polytope in the space whose dimension is n-3. n-3 because there are 3 conservation properties here. For example, the total area of this is fixed. As you can see, that means that all of them are lying along certain hyperplane. So there are 3 such constraints, and as a result, we have 6 points here. In this case, you get a 3-dimensional polytope, and here it is. So every vertex of this polytope is one of these vectors that I described. Now from this polytope, it's called secondary polyhedron, you can draw a secondary fan. So for every face, you can draw a line perpendicular to it. And if 2 faces share an edge, then you draw a wedge connecting the two lines. So as a result, your space will be subdivided into cones. What does it have to do with our monopole problem? Well, remember that perimeter points parameterize, give us the parameters. And once perimeter values are fixed, then you can change the interior value, that's the modulus, and that moves you up and down this line. So each vertical line in this picture represents a moduli space, the infinite modulus that you can vary. So as a result, if you take this fan and project it down onto this associahedral face, namely, associahedral face corresponds to vertices which don't involve the interior points, subdivisions which don't involve the interior points. Then you will get a phase diagram of this, of these ALH spaces. Namely, within each subdivision, within each resulting cone, you have the same type of the space. But as you cross, you change the shape of your space, sometimes drastically. So to be more concrete, let me describe what you get in this case. You have E2 space, and you can change these parameters. 3 of them don't matter, and 2 are important. So by changing them, you move along this pentagon. And if you change it, for example, if you are sending this parameter to 0, so it becomes insignificant, then as a result, your space degenerates to effectively space with this Newton polygon. And that is E1 ALH space. If you move in this direction, you get another E1 ALH space. And of course, there is certain isometry relating these 2 edges. So in principle, you should glue these 2 edges. If you move directly down, then you end up with E1 tilde ALH space. And if you move in any of these directions, you get some degenerate space. It no longer has moduli. For example, even without 3 cross S1, if you send the radius of S1 to infinity, you end up with R4. But if you send the radius of S1 to 0, you get degenerate space. So now we have a nice connection. We can connect all ALH, ALG, ALF, and ALE spaces. Namely, we take this monowall moduli spaces that we have and interpret them, for example, this one, as 2 monowalls, charge 2 monopole with 2 + 2 singularities. And if I now open up one of the periods of the torus, I end up with R3 cross S1 and end up with a problem with 2 monopoles, 2 periodic monopoles with 4 singularities. That's a D4 space. And one can keep track of these respectively And as a result, one can now realize ALG spaces as limits of monopoles. So as a result, everything in this picture, except for Shah spaces, are monopole modular spaces or their limits. And one can carefully study which limits and extract various information about potentially the metrics on the spaces, their topology, their geometry. I mind you, today I describe these spaces really, and to understand these E7 and E8 spaces, you have to attend talk by Thomas Harris, which will be on Friday. So to summarize, Tesserons are these non-compact, 4 real dimensional hyperkähler manifolds with finite Pendragon number, or square integrable curvature. And they're all classified now. The classification matches classification of Penlevé equations, which is magical and probably very significant. All Tesserons are modular spaces of monopoles or their limits. And if you look at them, where do they come from? What is the minimal number of monopole modular spaces you need to know to recover everything else as a limit? Well, you need to know the A series. That's fairly straightforward. 1 monopole with k plus 1 singularities. D series, 2 centered monopole with k singularities. You need to know E8 ALG space to get the E series from it. And you need to know half K3, which is again triply periodic monopoles with some singularities. So what I hope I managed to convey today is that this monopole picture is actually very useful to organize all of these tesserons into one coherent picture and to see the connection between them. Well, I'll stop here.
Okay, thank you very much for beautiful classification.